Okay, so protection of aldehyde or ketones and ketones. All right, the most popular protecting group for the aldehyde or the ketone is this thing called ethylene glycol. And so we mix the aldehyde or ketone plus ethylene glycol. It's acidic conditions, and this forms an acetal, which looks like this, plus water. Okay, so this is how you would protect up an aldehyde or a ketone. And so the strategy would be you're trying to do a reaction, you're trying to do a synthesis. The molecule maybe has, maybe the ketone or aldehyde is incompatible with the reaction you're trying to carry out. Look at that, look at an example of that in a minute. So this is how you knock the aldehyde or ketone out temporarily as an acetal. Then you do your business elsewhere in the molecule, and then you bring the aldehyde or ketone back. So this would be the deprotection. You have the acetal, and you mix that with water, and acid must be present. And so this is going to regenerate the aldehyde or ketone that you started with, and it's going to regenerate that ethylene glycol. So it's the conditions for the deep protection are water and acid. Please remember that water and acid, both of them must be present. It can't just be water. It can't just be acid. Okay, so that's protection of aldehydes or ketones. Very, very related to that would be the protection of a diol. So, we have lots of reactions, or we've talked about a couple of reactions where the OH group is not compatible with something we're trying to do. What I'm really thinking about is the Grignard reagent, right? Because when we use a Grignard reagent, no OH, NH, or SH anywhere. So if the molecule has this diol functionality and we want to run a Grignard reaction operating on some other part of the molecule, we have to protect the diol up, because when we use a Grignard, no OH, NH, or SH anywhere. Okay, so I could take something, I could take a 1,2-diol, and add acetone to it, or some cheap and non-exotic aldehyde or ketone. Acid conditions, well, that's just this, right? We get this acetal, but the virtue of this reaction is that this is no longer an alcohol. So do you see any OH, NH, or SH protons here? No, you don't. So the offending OH and NH protons have been removed. We could also try with something that is a little bit more exotic. Say if we tried a 1,3-diol, maybe something like that, right? This is a 1,3-diol that we wanted to protect up. Again, we would react this with some cheap and non-exotic aldehyde or ketone such as acetone, acidic conditions, and we get oxygen, oxygen, and this carbon right here, I'm going to put a dot on him, is here with these two methyl groups. And so again, what we've done is we've protected up the diol, but one of the things to notice here is that the only reason this works, this protection of a diol, is because you get a nice 5-membered ring here, thermodynamically stable, and nice 6-membered ring here, also thermodynamically stable. You can't protect up any, can't really protect up any other kind of dial other than this 1-2 or 1-3 because you're not going to get a nice thermodynamically stable 5 or 6-membered ring. Okay, and now D protection, because I've kind of run out of room. Let's just write it over here. D protection. It would just be the reverse, is that you have the acetal, you have the protected up acetal, add water to it, add acid to it, and the diol will be regenerated, as will the protecting ketone, right? So these two manifolds of reactions are very related. You protect an aldehyde or a ketone with a 1,2 diol. You protect a 1,2 diol with an aldehyde or a ketone. So they're very comparable. Okay. So let's try some synthesis problems, and let's see the context in which we would use this protection and deprotection strategy. Oh, by the way, I'm taking these problems from this handout, and I will post this handout online. And as usual in the discussion, there's much more stuff that we could ever get to here, so there will be more problems for you to work out on your own. Okay, so let's try the synthesis problem here. How would you go from this guy to this guy? Okay, so here's a classic setting, a classic and pretty easy to understand application of protection of aldehydes or ketones. So if you look at the reactant, look at the target, look at the starting material, look at the target. Clearly what has happened is the ketone, damn shadow, the ketone has undergone the addition of a methyl group, whereas absolutely nothing has happened to the aldehyde. So this is your big clue that protection was involved. So what you want to do is protect up this alcohol, this ketone, leave the aldehyde exposed. Sorry, you want to protect up this aldehyde, leave the ketone exposed, do your business with this ketone, and then regenerate the aldehyde. Okay, and so what I would do here is react the starting material with that ethylene glycol, and the aldehyde would undergo reaction, but not the ketone. And so it's worth pausing for a minute to wonder why. You know, one of my favorite epithets is to say that the molecules don't have a brain. They're not psychic. They can't read your mind. They don't know that they're supposed to react in this or that and the other way because you want them to. So is this an exception? Is the aldehyde psychic? Did it know to when I fed this molecule that this 1,2 diol, did the molecule know to protect up the aldehyde and not the ketone because that's what I wanted to happen? Not at all. So why is it that the aldehyde got protected and not the ketone? So give you a few seconds to think about reasons for that. Why did the aldehyde get protected and not the ketone? Sterics, right? The aldehyde is more reactive than the ketone for steric reasons. That the carbonyl carbon of the ketone is a lot more junked up with this methyl group. The aldehyde is protected, the aldehyde is defended by only this teeny tiny hydrogen. So in general, aldehydes are more reactive than ketones because of the fact that aldehydes are more sterically free than ketones are. So this is not psychic, right? This is aldehydes are more reactive than ketones for steric reasons. Okay, so I protected up my aldehyde. Now I can do my business with the ketone, and my business means bringing in a methyl group. And what is the reagent that is going to bring in the methyl? So what am I writing above and below the arrow there? What is going to bring in that methyl? Thinking about what that might be? How about the Grignard reagent, methyl magnesium iodide? Right, and remember, we think of the Grignard reagent as, we think of it as it has a negative charge on the carbon, and the MgI stuff sticks together and is always a positive charge. It's not really an ionic compound, but this is how it reacts. And so that methyl group goes in, we get this OMGI stuff that looks like that, but no reaction with this acetal over there, because that's an ether, and Grignard reagents don't react with ether. I'm done with the protection. I've introduced the group that I wanted to introduce, and now I can get rid of it. By deprotection, I add acid and water, H3O+, which is the same as saying acid and water. So that's the deprotection. And that H3O+ also works up the Grignard reaction mixture. So this is just an example of how how I have a molecule that has two carbonyl groups in it. I want something to happen to only one of them, so I protect the more reactive one, and then do my business on the less reactive one, and then bring the original carbonyls back. Okay, so hope that worked out. Let's try another synthesis problem that involves protection and deprotection. Okay, so here we're going to try, how would we convert cyclohexanone and this guy, which would be called 3-bromo propane 1,2-diol, and our target molecule would be this. Okay, the target molecule we're trying to make is this alpha keto acid. Okay, so once again, we see these three carbons here. I'm going to put a dot on them. These three carbons are clearly these guys. And so it looks like this molecule was somehow attached to this carbonyl carbon, and it made an alcohol. Well, we have lots of ways of making an alcohol, and the Grignard reagent is one way of creating an alcohol. But so we have to convert this guy into a Grignard reagent, but we can't have OH, NH, or SH anywhere when we're using a Grignard reagent. So we're going to have to protect up this 1,2-diol. All right, and then do our business elsewhere in the molecule, and then bring the 1,2-diol back. Okay, so what would we do is we take this guy, react him with some kind of cheap and unexotic aldehyde or ketone, such as acetone, and this is going to make this acetal. And we've just solved our problems as far as not being able to have any OH, NH, or SH because these OH groups have been temporarily masked as an ether. Now we can make the Grignard reagent, and we don't have to worry about having OH, NH, or SH. Okay, so we would be there now. And now let's do the Grignard reagent reaction on the cyclohexanone. So our first step here would be adding the cyclohexanone. That's going to give the Grignard reagent. I'll just write it out what we get here, I guess. We would get OMGBr with the Grignard reagent having attacked. So it looks something like that. Okay, and so now aqueous acid is going to not only liberate those OH groups, but it's also going to work up the Grignard reaction mixture. And so we would have that. Okay, so we protected up those diols because they're incompatible with the Grignard. We did our business elsewhere in the molecule, and then we brought the diols back. Okay, and now to finish off the synthesis, I know of a way to convert a primary alcohol to a carboxylic acid. I know a way to convert a secondary alcohol to a ketone, and I know a reagent that will leave a tertiary alcohol undisturbed. So what am I writing over that arrow? What's the reaction here? It's going to convert a primary alcohol to a carboxylic acid, a secondary alcohol to a ketone, and do nothing to a tertiary alcohol. What is it? Oh, it's the Jones oxidation. Chromium trioxide, sulfuric acid, and water. And I'm going to have to use excess of this. All right, so there's our synthesis. Okay, so let's finish up, for now anyway, let's finish up now with a big, huge synthesis problem that involves protection, deprotection, and other relevant reactions. Okay, so it would be, it's going to be kind of complicated and lengthy. This should be a 5-member ring. Oh, that looks very complicated, does it not? So how could we synthesize this molecule from 3 equivalents of cyclopentene, where all of the carbon in the target must come from something that we did with cyclopentene? Okay, so we can, just on our piece of scratch paper here, let's just write out strategy. And then we can finish up with the synthesis. So I'm looking at this and I see, oh, that's an acetal, right? It's an sp3 hybridized carbon bonded to 2 oxygens. And so this is an acetal. And how do I make an acetal? It's it's 2 equivalents of OH group plus a aldehyde or ketone. So it's going to be this. The last steps of our synthesis it's going to be this. It's 5-membered ring. So this plus acid is going to give this acetal. So it would be like as if we were protecting up this ketone with this 1,2 diol. Okay, and now what about something like this? Where is this coming from? Well, it's a ketone, and we know how to make a ketone. Ketone is made by oxidation of an alcohol. So if we could only make this alcohol, we could oxidize it to that ketone. And what I see here is this is an alcohol where the carbon next to the alcoholic carbon has something that I can interpret as the remnant of the nucleophile. And so this is going to be opening of an epoxide with a Grignard reagent. Okay, so there's our synthesis. There's our strategy. Is we take 1 mole of this, make it an epoxide. We take the second mole of this, make it into a Grignard reagent. We take the third mole of this and make it into this 1,2-diol, and then bring them all together at the end. Okay, so let's start writing out our synthetic steps. Let's first of all go for this Grignard reaction here. So you would take cyclopentene and you want to make an epoxide. And so how do we make an epoxide? What's the reagent that epoxidizes an alkene? Thinking about that? Yeah, that could be MCPBA. It makes this epoxide like that. Okay, and so we made him. Now we want to make the Grignard reagent. And so this Grignard reagent would be made by reacting magnesium with corresponding halide. I'm going to put Cl there. And so would we know how to convert this guy to something that had Cl on it? Oh yeah, that's an orgo-1 reaction. That would be, we could use HCl, and we would get this. Right, remember that from orgo-1? Okay, so that's the orgo-1 way of making HCl. The orgo-2 way of making this chlorocyclopentane would be to take this guy and react him with lithium aluminum hydride, right? That's a reducing agent. This is a basic nucleophile. This doesn't have a more hindered side or a less hindered side. So both sides would be attacked, and it doesn't really matter which one. So it would be first step that, second step H2O, and we would get this, right? That's opening of the epoxide. This is reduction. Notice this carbon starts life with 1 hydrogen. He has 1 hydrogen at the end. This carbon starts life with 1 hydrogen. Now he has 2 hydrogens. That's reduction, more bonds to hydrogen. And do we know how to convert an alcohol to a chloride orgo-2 style? Yeah, that would be that thionyl chloride and pyridine. So we want to make this chlorocyclopentane. We have an orgo-1 way of making it and an orgo-2 way of making it. Okay, and so now we would take this guy and then react him with magnesium to make our Grignard reagent. Okay, so this guy plus the cyclopentyl magnesium chloride followed by acid workup, H3O plus, is going to open that epoxide on the less hindered side. It doesn't really matter in this case. And so this is how we would make this. Okay, now how would we make, let's put a little bar here. Now we also need to make this diol from our third equivalent of cyclopentene. And we know how to do it. This is an orgo-1 reaction, but we could also do it orgo 2 style. So how do you take an alkene and convert it to a diol? Remember that? That's what? Osmolation followed by workup. But we also have an orgo 2 way of making a diol. We have an orgo 2 way of making this very same thing, which we would use MCPBA, make that epoxide, and then open the epoxide up under either acidic or basic conditions, right? This is chemistry was covered early in the term. So maybe I could use H3O plus. So that's how we would make this guy orgo 2 style. Okay, we're ready to finish up. Next, PCC is going to oxidize the alcohol to a ketone. And then, last step, reaction of this ketone with the diol that we made. Reaction of the ketone with the diol that we made. And acid, and that completes our synthesis. Okay.